The universe has long captivated us with its immense scales of distance and time. In recent times, giant new telescopes have allowed us to cast our gaze into the deepest reaches of the known universe. Astronomers have concluded that the stars and galaxies that stretch out to the limits of our vision may represent only a small fraction of all there is. They are pioneering bold new theories that describe a universe that extends far beyond the limits of our vision. Where does it all end? Where do we fit within it? A remote outpost in the Andes Mountains. Here, astronomers are opening a whole new window onto the universe. The Rubin telescope, with its giant state-of-the-art mirror, will send a vast stream of data to a global network of processing centers and supercomputers. Its target: dim objects racing through our solar system. Stars in distant galaxies exploding. Or flying into violent collisions. These blasts of energy from distant corners of creation are messages from a universe that is evolving in ways we can scarcely comprehend. They are propelling us into a new age of advanced scientific theories about the very nature of time and space. Theories that challenge philosophical assumptions that have guided us since ancient times. The Greeks were the first to see natural events as phenomena, subject to human investigation, rather than the whims of the gods. One philosopher and skywatcher, Anaxagoras, went so far as to say that meteors are made of materials found on Earth, and therefore might have actually come from the Earth. To observers back then, the world was made of 4 classical elements: earth, water, air, and fire. The philosopher Aristotle proposed that the realm of Earth is fundamentally distinct from that of the stars. He argued that stars are made of a 5th element, unchanging and incorruptible, called quintessence, or space. The realm of the stars, in Aristotle's view, was the home of deities, arranged in a succession of spherical regions surrounding the Earth. What would happen if a warrior traveled to the outermost region and tossed a spear? Where would it go? It would not fly off on an infinite journey, Aristotle said. Rather, it would join the motion of the stars in a crystalline sphere that encircled the Earth. He assumed the universe, with Earth as its focus, was limited in extent, finite in size. Aristotle grappled with an implicit challenge to this view that would one day transform science. Nearly 2 centuries before, the Greek mathematician Pythagoras and his followers began to see numerical relationships as the key to understanding the world around them. But in their investigation of geometric shapes, they discovered that some important ratios could not be expressed in simple numbers. One is the circumference of a circle to its diameter, called pi. Computer scientists recently calculated pi to 5 trillion digits, confirming what the Greeks learned. There are no repeating patterns and no ending in sight. The discovery of the so-called irrational numbers like pi was so disturbing. Legend has it that one member of the Pythagorean cult, Hippasus, was drowned at sea for divulging their existence. To Aristotle, the idea of infinity evoked the chaos from which the world emerged. A primordial state with no natural laws or limits, devoid of all form and content. To preserve the idea that the universe has a form and limits, Aristotle crafted an historic distinction. On the one hand, he pointed to the irrational numbers such as pi. Each new calculation results in an additional digit, but the final number in the string can never be reached. Aristotle dismissed it as potentially infinite. Far more important, in his view, was a value called the actually infinite. To understand it, take a ruler and try calculating the number of subdivisions within subdivisions. There is a final number, Aristotle said, though we will never identify it. Aristotle reserved that knowledge for the so-called prime mover, the one who created the universe and operates beyond our meager capacities. This idea became the basis for the cosmological or first cause argument for the existence of God. Another century later, Archimedes incorporated actual infinity into measurements of curved lines and volumes. His method boiled down to a process of summation. Place a triangle inside a circle. Turn it into a square, then a pentagon, and so on. As the number of sides increases to infinity, their combined lengths equal the circumference of a circle. By slicing and dicing curves into an infinite number of straight lines, he was able to compare a variety of curves, areas, and volumes. Archimedes anticipated techniques developed 2,000 years later. And yet, his ideas on infinity did not carry forward. Instead, it was Aristotle's idea of a finite universe, with Earth seated firmly at the center, that passed into the Christian era. Not everyone agreed. Islamic, Hindu, and even some Western thinkers posed alternate views that included infinite space. In European circles, the idea of a limited universe came into question during the Renaissance. In 1543, the Polish astronomer Nicholas Copernicus argued that Earth orbits the Sun, not the other way around. The old Greek spheres began to fall by the wayside when the astronomer Tycho Brahe spotted a supernova in 1572. Then a comet. These objects seem to behave independently of the other stars. Still, church leaders frowned on any attempt to extend the boundaries of the universe, for that encroached on the unique province of God. That didn't stop a monk named Giordano Bruno, who traveled Europe in the height of the Inquisition, proclaiming an infinite universe. He was burned at the stake for this and other heresies in the year 1600. 9 years later, in 1609, Galileo Galilei used the first astronomical telescope to show that the solar system and the universe are much larger than we thought. Galileo was forced to recant his views. Still, the reality of a much larger cosmos had begun to sink in. John Milton spoke for a generation of scientists and poets in his 17th century epic Paradise Lost. When I behold this goodly frame, this world of heaven and earth consisting, and compute their magnitudes, this earth, a spot, a grain, an atom. At the end of the 19th century, the mathematician Georg Cantor sought once and for all to take metaphysics out of mathematics. He became known for folding finite and infinite numbers into a unified theory of number sets, considered a foundation of modern math. To show how it works, his defenders conjured up this grand hotel. You arrive to find it's booked solid. But you're in luck, because here there is an infinite number of rooms. The manager assigns you to room number 1 and directs you down the corridor. Then she goes to work, shifting the guest in room 1 to room 2, room 2 to room 3, 3 to 4, and so on. So in this hotel, there's a number set that includes an infinite number of rooms. Then there's that same set plus your room. Two infinite sets, yet one is a subset of the other. Being able to use infinite sets of different sizes allowed mathematicians to design equations describing continuous motion and change over time. Even as mathematicians embraced infinity, scientists still had trouble squaring it with physical reality. Albert Einstein, for one, believed that if the universe had no limits, then the night sky would be filled with dense starlight, shining from every direction. We'd reel from the effects of infinite gravity. Instead, much like Aristotle with his warrior, Einstein believed that space was, by its nature, curved. Parallel lines would always meet, and beams of light inevitably returned to their source. As far as astronomers could see, the universe had its limits. It consisted of a flat disk of stars, the Milky Way, an island universe in which the solar system resides. That view crumbled in the 1920s. Edwin Hubble and Milt Humason used the new 100-inch telescope on Mount Wilson in California to look at mysterious fuzzy patches of sky called nebulae. They found that some of these patches were galaxies like the Milky Way and very far away. What's more, the farther away they are, the faster they are moving away from us. This fact, known as Hubble's law, led to an inescapable conclusion: that the universe began at a singular moment in time, a violent primordial event called the Big Bang. This view rested on four main pillars. 1. That the universe is expanding in all directions. If you turned the clock back, you'd see that everything had a common starting point. 2. It established a time frame for the formation of stars, galaxies, and the distribution of matter on large scales. 3. It established a time frame for the chemical evolution of the universe, with light elements like hydrogen dominating the early universe, and heavier elements generated over time in the life and death of stars. Finally, it described the universe in its primordial state. In the wake of the Big Bang, the universe was filled with a cloud of extremely hot gas that scattered all light. As the universe cooled and the first atoms formed, the cloud dissipated. Light was able to move freely about. Over time, as the universe expanded, the spectral signature of this light would have shifted into the microwave portion of the electromagnetic spectrum. In one of the great accidental discoveries of all time, a pair of physicists spotted this primordial light back in the 1960s. Bell Labs had built a giant horn-shaped antenna as part of a long-distance radio transmission system. Arno Penzias and Robert Wilson pointed this contraption into space. Wherever they aimed, they picked up excessive microwave noise. That noise, part of the static on many old-style televisions, is the echo of the Big Bang. Decades later, the Hubble Space Telescope launched into orbit on April 24, 1990, in one of the most important scientific milestones of our time. Another notable launch took place 5 months earlier. The Cosmic Observation Background Explorer, COBE for short. It found that the microwave background signal in space contains a subtle pattern of hot and cold spots. Later missions mapped an even more detailed pattern, including this image from the European Planck Observatory. If scientists can find the source of this pattern, they might learn not only about how the universe began, but where it's going. At the European Large Hadron Collider, they are sending protons racing in opposite directions in a circular tunnel 27 kilometers long. When these particles reach velocities just short of the speed of light, they are sent into a violent collision. A fireball erupts, reaching a temperature exceeding 2 trillion degrees centigrade. As far as we know, the last time anything in our universe was that hot was about a millionth of a second after its birth. The splatter of subatomic particles forms a super-hot soup of quarks and gluons. The thinking is that a primordial energy field that spawned the Big Bang was patterned with tiny fluctuations. These fluctuations generated pressure waves, or ripples, that passed through the ultra-dense quark-gluon mix. As the universe expanded, these ripples would have been imprinted on the distribution of matter, on the largest of scales. To test this idea, astronomers set out to literally map the universe in 3 dimensions. In an age of computer-controlled telescopes and automated observing, astronomers targeted a large fraction of the sky. The Sloan Digital Sky Survey in the mountains of New Mexico set the standard for large-scale cosmic cartography. A series of steel plates are drilled with holes that exactly match the locations of galaxies in the night sky. After plugging fiber optic sensors into the holes, the plates are loaded into the telescope. It then captures the light of hundreds of galaxies per night, gathering information about their brightness and distance from Earth. From this data, astronomers are assembling a whole new cosmic atlas in 3 dimensions. Traveling out into the data, we pass beyond our remote corner of the Milky Way. we enter a collection of 20-odd galaxies known as the Local Group, our cosmic neighborhood. Our path takes us some 50 million light-years away to the densely packed Virgo supercluster, the nearest intergalactic city. Beyond Virgo, galaxies line up in walls and arcs, bounded by vast empty voids. The goal in ever larger survey projects is to trace the evolution of these structures all the way back to their beginnings. Looking north, the Sloan Digital Sky Survey has mapped galaxies out to 1/3 the distance to our visible horizon. Astronomers are now leaping beyond that with projects based in the mountains of Chile. The Dark Energy Survey uses one of the largest cameras in the world to divide the field of view into 62 high-resolution detectors. Each one captures countless thousands of celestial objects extending halfway across the visible universe. Night after night, month after month, the exposures pile up across a survey area that covers 1/4 of the southern sky, or 1/8 of the entire sky as seen from Earth. The Rubin telescope on a nearby mountain expands that to 1/2 the sky seen from Earth. How far we can see into the deep universe is determined by the speed of light, how far the light of distant objects would have traveled since the Big Bang. Using Hubble and other modern telescopes, astronomers have placed that time at 13.7 billion years ago. Taking into account the expansion of space ever since, the radius of the visible universe, our visible horizon, extends out to 46 billion light-years from Earth. If you look in opposite directions, the most distant galaxies discovered by the Hubble Space Telescope are actually 92 billion light-years from each other. The horizons of those galaxies would stretch to 138 billion light-years from Earth. Where does it end? In fact, our 92 billion light-year wide patch, the visible universe, may be a mere speck within the universe as a whole. That's the conclusion of a dramatic new theory designed to address questions about the nature of the Big Bang. 1. How did the universe get so large so quickly? And 2. How did it get so smooth? In every direction you look, the density of galaxies is the same on large scales. Whatever process flung the universe outward must have somehow blended it in its earliest moments. The new theory, called inflation, is based on the discovery that space is not, as scientists once thought, just the absence of matter. It is actually seething with energy in the form of particles of opposite charge, matter and antimatter. Back in the 1980s, the physicist Alan Guth proposed that in primordial times, an energy field embedded in the vacuum of space suddenly tipped into a higher energy state. causing space and time to literally inflate, and our universe to burst forth. The universe went from atomic size to cosmological size within an infinitesimally short time. As a result, according to Guth's calculation, the universe as a whole would have grown to some 10 billion trillion times the size of the observable universe. That's a 10 followed by 24 zeros. Put another way, an atom is to the observable universe as the observable universe is to the whole universe. The fury of cosmic inflation helps explain the immense size and smoothness of the cosmos. But this basic theory still does not get us beyond the idea, held by thinkers from Aristotle to Einstein, that the universe is closed, finite in size, even if mind-bogglingly large. Recent versions of inflationary theory have begun to force concepts of infinity back into our popular cosmology. Astronomers have known for decades that the amount of matter observed in distant galaxies does not supply enough gravity to hold these spinning structures together. There is a missing ingredient that we just do not see. Its identity still unknown. Scientists call it dark matter. By adding dark matter into supercomputer simulations of cosmic evolution, scientists have been able to recreate the gravitational fields needed to form the large-scale structures we observe. Astronomers wanted to know, is the gravity of dark matter enough to one day slow the cosmic expansion to a stop? To answer this question, they sought to refine their measurements of cosmic expansion by using a new type of distance marker called a Type 1a supernova. It emerges from the charred remains of a sun-like star called a white dwarf. If this star takes on mass by drawing it from another star, it may grow to a critical threshold and explode. Type 1a supernovae are thought to shine at uniform intensities throughout the universe. So, if astronomers measure differences in their brightness at varying distances, that could indicate a change in the cosmic expansion rate over time. To their surprise, the data showed that the universe as a whole is not only expanding, it's actually accelerating outward. The culprit is thought to be energy welling up in minute quantities from the vacuum of space. As the universe expands, the force exerted by these particles increases over time, enough to push space outward across the whole universe. This so-called dark energy now amounts to an astonishing 3/4 of all the matter and energy in the universe. If it's similar to what drove inflation in the early moments of the Big Bang, then our universe may exist in a far broader cosmic context than we've imagined. There is a version of inflationary theory that suggests we live in one of many universes that emerged and coexist side by side, like bubbles continually rising up from an infinitely vast quantum vacuum. They are expanding throughout an endless ocean of space and time. A related idea theorizes a cosmic landscape unfolding in vast fractal patterns. From this new perspective, our universe, however we define it, is incomprehensibly small. As if that's not mind-boggling enough, yet another version of inflation upends our entire conception of time and space. Astronomers at the Rubin and other observatories will be scanning the heavens for a breed of black holes that would have been born moments after the universe burst forth. Some might have sown the seeds of the first galaxies, growing over time to millions, even billions of times the mass of the Sun. Others, far more numerous, and as small as the Moon, were left to roam the cosmos, moving silently amid the luminous dust lanes and glowing stars of galaxies like ours. The idea is to scan billions of stars in the Milky Way and other galaxies. If a black hole passes through our line of sight, a star behind it will dim, then brighten. The discovery of these objects would lend insight into one of inflation's wilder predictions. That in the ultra-dense conditions of early times, more than one universe would have inflated. Perhaps within one of those primordial black holes. From our vantage point on the outside, these objects would appear simply as black holes. If you could go inside, a baby universe would appear to be expanding outward, much like our own. Back in Galileo's time, most skywatchers saw the universe as an assemblage of stars that surrounded the Earth in relatively close proximity. He showed, instead, that stars are far removed from our planet. Imagine how Galileo would have reacted to this image of Earth. Captured in the year 1979 by the spacecraft Voyager 2 as it passed by Neptune. Since Galileo's time, our Earth has gone from the center of all things to a pale blue dot, lost in the vastness of space. We now know it is set within a universe of galaxies. Clusters of galaxies. And beyond them, vast luminous walls and filaments of matter. Today's ideas about the size of the universe amount to a quantum leap in our sense of scale. By extending these structures far, far beyond our horizon, perhaps touching on the infinite. Do our discoveries push us on this tiny, out-of-the-way planet into an ever smaller corner of creation? Or does our ability to comprehend and imagine the far limits of time and space somehow expand our importance? In the grand scheme of things,